I'm Nathan Sanders from California State Monterey Bay, and I conducted research on the performance of model averaging relative to individual models for testing Hormesis. So some background is Hormesis is a biological phenomenon that low doses of carcinogen may reduce the risk of cancer while high doses increase the risk. For the plots, the x-axis is doses of carcinogen and y-axis is probability of cancer. Right has a hormetic trend and the left has a monotonic trend. So model averaging is a statistical method which utilizes multiple models for statistical inference. A simpler model with better fit has greater contribution in the MA procedure, and we use weight and AIC to determine this. In toxicology research, many researchers use a single dose response model, and the problem with this is that it can lead to low statistical power in some cases of hormesis. So for our hypothesis testing, we define theta as the difference between the zero dose, pi sub 0, and the first non-zero dose, pi sub 1. When theta is less than or equal to 0, we consider that as a monotonic trend, and if theta is greater than 0, we consider that as a hormetic trend. Here are 5 different models for model averaging based on the logistic model pi of x. And for our model M3, M4, and M5, we allow discontinuity on the dose response curve. For our model averaging procedure, we bootstrap the original sample and fit our 5 models to that sample and calculate the log likelihood for each model, calculate the AIC for each model, calculate the weight for each model. From then, we're able to generate a theta hat estimate for our model averaging based on the weight and theta hat for each of the following models. We then obtain a bootstrap distribution of our model averaging estimate by bootstrapping it 1,000 times. From then, we take the 5th percentile of the distribution, and if that 5th percentile is all positive, then we can conclude for hormesis. For simulations, we created 16 different scenarios, and for our first 1 through 5 scenarios, we wanted to test type 1 error, so we made the truth be monotonic, and for scenarios 6 through 7, we made it so that the truth is based on model 1. For scenarios 8 through 13, the truth is based on model 2. For scenarios 14 through 16, we picked arbitrary points that had a hormetic trend. So here are our simulation results. For scenarios 1 through 5, the truth is monotonic, so we set a significance value of 0.05. And specifically for scenario 3, model 3, we see that it violates type 1 error significantly. The good thing is our model averaging, which is in purple, does not get that much contribution from model 3, so it relieves that type 1 error rate. For scenarios 6 through 7, we see when the truth is based on model 1, which is in red, we see model 1 performs really well. However, when we get to scenarios 14 through 16, we see that model 1 does not conclude hormesis at all. But in that case, model 1 did not play a big role in the model averaging method. So for our discussion, we noticed that an individual model may violate our significance value, and our model averaging method can actually relieve that violation. When the truth is the simplest, for example in scenarios 6 through 7, the use of the true model is best. In practice, the use of the model averaging leads to robust results, an example close to the best individual outcome across the scenarios. For our future work, we want to research other weighting methods such as KIC or BIC, which penalizes complex models more than AIC. We also want to consider a smaller number of models for our model averaging method. An example, M4 was always inferior to M5. And finally, here are some sources that we used for our research.